guztioi, buenos días a todos. Bueno, primero, el modelo Ramírez, celebrado de Chavales, recochea. Entonces, vamos a dar comienzo a la primera conferencia plenaria de hoy. Entonces, el ponente es el doctor Baran. Él realizó su tesis doctoral en la Universidad Técnica de Dinamarca. Desde entonces ha estado trabajando en la Facultad de Ingeniería y Tecnología de la Universidad de Twente en Holanda. Sus ámbitos de interés investigadora se centran en el procesado de composites con fibra, el modelado del daño y de composites, el modelado matemático de problemas multifísicos y en el desarrollo y aplicación de métodos computacionales avanzados. Y el título de la ponencia que va a llevar a cabo hoy es How to Overcome Challenges in Reliable Composite Manufacturing. Please, Dr. Baran.
Thank you. Yeah. Good morning, everyone. Thank you very much, Liron, for a nice introduction. First of all, I'm really honored and appreciate the opportunity, very much opportunity to show some of our work in this beautiful Congress and in San Sebastián. My name is İsmet Baran, and my research in general helps our community to have more sustainable world of future using lightweight and high performance composites. Now I'm going to show you how we can actually tackle some of the challenges in reliable manufacturing of composites. The sky is the limit for composites, as we all know. They are applied in various industries, such as very large wind turbine blades, really complex shape window profiles, and various lightweight designs in construction, automotive, aircraft, as well as aerospace industries. In all these industries, the major requirement from a product quality can differ. For example, for window profiles, the dimensional accuracy is very critical. On the other hand, long-term mechanical performance is the case for wind turbine blades. Similarly, we have the same variety in handling the reliability in composite materials used in various industries. For example, economic issues are critical for wind turbine industry because of the competition between wind energy and the fossil fuels. And safety, on the other hand, is the case for aircraft and a bit mix for automotive industry. So in all cases, the reliability of the composite material is heavily dependent on the manufacturing process, the quality of the manufacturing process. I would like to get your attention on how we can actually benefit from lightweight design of composites. So I would like to give an example. As you probably already know that world's one of the largest wind farm has recently been established in North Sea, just very close by Netherlands. And this wind farm actually has 150 wind turbines, which generates electricity of 2.6 terawatt hour per year, which is sufficient for 1.5 million people annually. And using the lightweight design of rotor blades, actually we can reduce the CO2 emission approximately 1.25 million metric ton per year, which is equivalent of having 270,000 cars off the road. So this is amazing and serious action indeed towards Paris Climate Agreement. So where we have strict goal to limit the global temperature rise to 2 degrees C. However, in order to continue competition with fossil fuels and contribute to the Paris Climate Agreement, we need reliable manufacturing of wind turbine blades made of composites, because they need a minimum of 20 years of lifetime. Having said that, let's look at a lifeline of a composite structure. So manufacturing of composites obviously start with combining fiber reinforcements and the matrix material. Here I refer matrix material as the thermosetting one, and I will use this term throughout my presentation. Usually a mold is used in which the fiber reinforcements are impregnated, and during the process we have stresses occur due to the anisotropic behavior of the ply in micro and macro level, as well as a competition between thermal and chemical shrinkage strains. So after process, obviously we have the product, and usually in the product we have residual stresses which may cause matrix cracking or delamination, even in series or in premature format. In addition, we may have void, resin-rich areas or dry spots because of the poor impregnation, as you can imagine. And the question is, it's obvious that there's a direct influence of this lifeline on the mechanical performance during the service life applications. So here I have an example of changing the failure mechanism of a composite material. So here we have a simple short beam shear specimen in 3-point bending loading condition, and we have a matrix crack and a small porosity in the specimen. So after performing some simple tests, some of the groups actually failed in tensile mode with 750 newtons force at fracture. And here is the fracture zone. On the other hand, some of the specimens failed in shear mode exactly at the matrix crack region, where we have 520 Newton force at fracture. So it's clear that there's a 25% reduction in force at fracture having the same type of defects in the specimen. So this is a coupon level which we can control as much as details we can. However, if we have a question, something like that, can we know manufacturing-induced defects and their effects on the large-scale components? So it's obvious that unknown defects and their unknown effects on the large scale can cause unexpected catastrophic failures during in-service life applications. In addition, I have an example that a small crack in a wind turbine blade can yield in 25 million United States dollars for downtime and repairing costs. which is reported in 2010. And it's clear that based on the process-induced aspects, the reliability and the lifetime of our composite can reduce significantly. And these facts actually show that the costs of inaction are higher than the cost of action. So that's why we need to take serious and immediate actions towards professionalism in composite manufacturing. So this will obviously pave the road for reaching Industry 4.0, which is considered nowadays computerizing the manufacturing processes. So we can achieve this by understanding the material systems and process dynamics, describing mathematical relations for the material and the process, translating these two in a numerical simulation platforms where we can predict the critical physical phenomena taking place during the process. And finally, using the developed framework, we can optimize the process in a systematic way. Now, I'm going to show you some activities addressing first three topics by taking an example of a pultrusion process, which is in principle a simple process to manufacture constant cross-sectional profiles in a continuous and automated way. So with the pultrusion process, we have really high fiber volume content, up to 70, even 80% by volume. So in pultrusion process, the fiber reinforcements are pulled through a resin bath or a resin injection chamber, in which the fibers are obviously impregnated. And then the wetted out fiber reinforcements enter heating or forming die, in which the matrix material changes its state from liquid to solid via a gel state. So at the end of the process, with the help of a saw mechanism, the product is cut into desired length in meters. So in principle, we can manufacture kilometers of profiles using this efficient process. I'd like to introduce some of the history of pultrusion process. So this is, I found it interesting. So it was first invented in 1951 for producing shafts for fishing rods, so simple application. And Goldsworthy actually introduced a better version in 1959 for producing general composite profiles in various cross-sections. And in 1971, the industrialized pultrusion process setup was invented. And nowadays, we have most of the pultrusion lines in industry look like to this format. And the last improvement that I found from literature was that after 40 years later, in 2011, Janssen and co-workers actually invented a curved pultrusion in which constant cross-sectional profiles can be manufactured using this setup with a certain radius. Having this history of pultrusion in mind, we do see some examples of pultruded profiles. On the left-hand side, we do see the curved one, and on the right-hand side, various pultruded profiles with different cross-sectional shapes. Nowadays, pultruded profiles are used in wind energy, and especially in wind turbine blades. Really thick pultruded unidirectional profiles are used because of their consistent product quality and high fiber volume ratio. We do see an example, pultruded wedge embedded in the root section of a wind turbine blade. So we said it's a simple process. We are just pulling the fibers. But in reality, it's a really complex process, as you can imagine, because of the diverse interaction between resin flow during impregnation, heat transfer, chemical reactions, and especially the solid mechanics at different scales from micro to macro. During the process, we have a temperature evolution. We have degree of cure. We have the viscosity evolution, from which we can define the gelation point of our thermosetting composite. We have glass transition temperature that is also evolved as a function of temperature and degree of cure. And these are the main physical phenomena taking place that I can plot here. Of course, on top of that, we have stresses and interfacial bonding quality developments. But based on these curves, we can define the state of our matrix material. So up to gelation, we have viscous form. From gelation to the point where the temperature becomes lower than the glass transition temperature, we define rubbery zone. And after the point where we have the temperature smaller than glass transition temperature, TG, we define it glassy or solid state. So based on these complex transitions and development of different physical phenomena, there are some challenges in manufacturing of pultruded profiles. So as we discussed previously, we have residual stresses, and because of residual stresses, we have shape deformations and variations in properties in different levels, from micro to macro again. So because of residual stresses actually during the process, so it's very important that we may have severe internal cracks, as well as, so this is a micrograph of a crack, which is actually very severe, not a premature crack. And this is really amazing. A delamination occurred during the process. And in the end of the process, we might have warpage. So dimensional stability is lost here. So if you look at the internal structure briefly from micro-CT analysis, we do see some resin-rich areas between the fiber rovings. So in principle, the fiber rovings should be aligned in between the guiding plate and the pulling unit. If this alignment is not perfect, the fiber rovings during the pultrusion can wander to a local place such that we have resin-rich areas with really low fiber volume content. And we do see these resin-rich areas here, and around resin-rich areas, we have severe fiber misalignment in the in-plane and out-of-plane directions. And if we continue to the micro-CT analysis, we observed during our ongoing work 3D cracks and porosities. And these 3D cracks actually are taking place due to the highly excessive shrinkage of the resin-rich areas. So during processing, because of the chemical shrinkage, the resin shrinks more and separated from the fiber roving regions. That's why we have these true thickness along the pulling direction 3D cracks. And it's amazing to see that these cracks actually are transforming. Their shape is changing because of this fiber misalignment. So in order to have, again, a reliable manufacturing of composites, we need to understand, describe, and predict these kind of physical phenomena during the process. So usually we start with material characterization. It's obvious that with the current state of the art, we can predict and analyze the chemorheology, thermokinetics, and thermomechanical properties evolving during the process. And here I have an example: cure kinetics, temperature and cure dependent elastic modulus, and the viscosity. So the idea is transferring all this data to numerical process simulations to predict the physical phenomena taking place during the process. The current state-of-the-art process modeling framework for pultrusion processes was developed by by coupling 3D thermochemical analysis with the 2D mechanical analysis. So in the 3D case, we calculate temperature and degree of cure fields and then map these fields to a 2D mechanical model. So in the mechanical model, we actually calculate the thermal and chemical strains and the evolution of mechanical properties using the temperature and cure dependent material data. And then up to now we have tried to answer some of the challenges during the pultrusion process. Now I'm going to show you some scientific efforts that we have made towards reliable manufacturing of composites. Shape deformations are very important for dimensional stability. Here we have an example of industrially pultruded angle profile, which is used in construction industry. And here the dimensional stability of the angle between the legs are very important. And this profile consists of unidirectional layer inside and outside matte layer, continuous filament matte, CFM. And the material was glass polyester. Using the developed process modeling framework, actually we can predict the evolution of springing inside the die mold and as well as in the post-die region during solid state cooling. And we compare the predicted springing angle with the measured angle from the profiles. And using the process model, we defined springing angle as a function of pulling speed, and it's obvious that the angle is increasing with an increase in pulling speed because of the high true thickness cure gradients. Similarly, we can predict the warpage in a rectangular hollow profile. So this profile is manufactured using a mandrel obuse. And using the simulation platform, actually we can, for instance, investigate the effect of total volumetric shrinkage of the resin material on the final warpage. So this is a very practical information for industry, such that they can modify their resin systems and to see their effect on the dimensional stability. Local fiber volume content distribution is very critical, as we saw it from the micro CT images. We have resin-rich areas between roving layers. And here I have an example of a real pultruded profile, relatively thick, 50 by 50 millimeters, full of UD. If we look at a region of interest of 3 by 5 millimeters, we do see a severe resin-rich areas between the roving layers. And the question is, so in that case, we don't have any crack, but we may have a premature crack. So the internal stress might be that high. So during the in-service loading condition, with a small loading, we might have a unexpected catastrophic failure. So the idea is that we can analyze this image using microscopy, optical microscopy, and embed it to the existing process model. So this is the picture of microscopy analysis and the image processing. We have only now fiber and resin distribution. However, the total pixel size is relatively too high for a finite element simulation. It's now 7 million pixels with a pixel size of 1.6 micron. So the idea is to average these pixels for a less amount of pixel size. So now, after averaging, we have 24,000 pixels, which is doable with the simulations and with an approximately 25 microns, so approximately diameter of one glass fiber, more or less. So now we know the local fiber volume distribution with the local mesh, and now we can embed this mesh to the existing cross-section of the model. So in the existing model, we have uniform fiber volume content with 55% for the fiber volume content. And if we add this local mesh here, so we have a specific distribution of the fiber volume distribution here, and the remaining region has a uniform fiber volume with 55% again. So in the numerical process simulations, we are using quarter model because of the symmetry boundary conditions. And the fiber distribution is in the x3 direction, which is in the out of plane with respect to the screen. Let's have a look at some results. So this is the stress distribution using the uniform fiber volume content. So this is transverse normal stress, and on the right hand side we have the transverse shear stresses. So it's obvious that we have tensile stress in the center because of curing takes place in a later stage but in a faster manner. For the maximum transverse shear stress, we have it in between center and the outer surface, and this is again due to the non-uniform curing of this relatively thick profile. Okay, let's investigate what would happen in the region of interest with the local mesh. Recall that we have local mesh here. This is the uniform stress distribution, and we are concentrating on this local region of interest. We have one result from uniform fiber volume content results, and it's obvious that all stress components are negative, so we have only compressive stresses in this region. With the local mesh, the stress field, as expected, changes significantly in terms of magnitude and the sign. So now we have tensile stresses in the pure matrix region domain. So with this combined macro and micro type of approach, actually we can investigate the internal stress level in the matrix dominated regions. So we can do it by displaying fiber volume content being less than 1% in the simulation, and then evaluate the von Mises stresses for the matrix region. And again, we can do this for also other stress components in transverse shear and out of plane normal stresses. And again, a significant change in stress was the case as expected. Non-uniform curing is obviously very important, as we discussed with the delamination during the process. If we have a partially cured region inside the material, and then it's very likely to have a delamination of the laminated composite during the process. And again, this is due to the fact that we have a competition between thermal strains and the chemical shrinkage strain. So this is the delaminated pultruded profile just after the pultrusion die, because of the fast contraction of the outer surfaces and a partial, actually non-cured center region. And this profile is pulled with really high pulling speed, especially to see this kind of delamination. Using the process models, actually we can determine which pulling speed should we use for specific part thickness. So it's obvious that we have a conflicting phenomena here. We would like to maximize the pulling speed as industry, but on the other hand, we don't want any delamination, or we don't want any high cure gradients through the thickness. So this is the plot of pulling speed, part thickness, and centerline degree of cure during the process. So it's obvious that for very thick profiles, we have to pull our profile really with slow speed. And for thin profiles, we can use the maximum capacity of our machine. So another way is to prevent non-uniform curing for thick profiles can be using a preheater before the pultrusion die. So let's have a look at an example of a really thick profile, 10 centimeters by 10 centimeters thick. And let's see the effect of using preheater on the curing and the residual stress formations. So we do see the preheater temperatures 40 and 60 degrees here, and without preheater temperature in the first case. And it's obvious that in all cases we have a non-uniform curing. But the magnitude of this non-uniformity is getting decreased if we increase the preheating temperature. And if you look at the cure distribution in the end of the process, we have partially cured regions without using preheater and a more uniform, actually a good curing for using preheating temperatures. And these are all reflected on the stress distribution as well. So here we quantified the effect of preheating on the residual stress distributions. So in total, approximately 50% reduction in tensile transverse stresses at center. So this is very important that, so the reason behind that is that, okay, uniform curing, but actually we have softer internal mechanical constraints inside the profile during processing. So we have less stiff constraint at glass state during the process. This is also reflected in transverse shear stresses. So a 70% reduction was obtained using the preheating temperature. So up to now, we have addressed 3 aspects for professionalism in manufacturing of composites, such as understanding, describing, and predicting the main phenomena, critical phenomena taking place during process. And now I would like to show you some optimization studies in which we can control the process in a systematic way using the developed process models. So now we have a well-defined process model. We took geometry information, material behavior, and the process parameters into account, and we verified our process model such that we can now use for process simulations and process control. One option using the process model is controlling the manufacturing inline. So I have here a block of model-based inline process control. So we are very active in this field, not for pultrusion, but for laser-assisted tape winding process, in which we are developing physics-based process model, and our aim is to calculate the nip point temperature. So here we have the nip point temperature between the tape and the substrate. We would like to calculate the nip point temperature in a fast and accurate way such that we can control the process inline. With the predictions using the model, we can provide optimum process parameters to the machine, and the machine controls the process for improved bonding quality. Because the bonding in between the tape and the substrate is heavily dependent on the temperature, as well as the contact pressure, intimate contact, and healing, so on. Other than this model-based inline process control, we can actually do, it's obvious that offline process optimization using deterministic and reliability-based approaches. I have some examples for pultrusion processes. So in pultrusion, we have discussed that we would like to maximize the pulling speed, minimize the true thickness cure gradients, and of course minimize the energy consumption. So in a optimization problem for pultrusion processes, we can define maximizing the pulling speed and minimizing the total energy consumption. And next to it, we can define several constraints. For instance, the maximum composite temperature during the process cannot excess 240 degrees C for degradation. And we can set a constraint on the degree of cure at the die exit, such as it should be at least 0.9, 90% cured at the die exit. And on top of that, we have several constraints on the geometrical and the process parameters. In this case, we are also optimizing a discrete number of heaters in the simulation. So this helps us to learn the machine from the optimization problem. So let's have a look at the results. Now, according to the results, we have three options with respect to the heater configuration. Actually, the process designer can select the number of heaters based on the pulling speed. Here we do see, for instance, if you would like to use 2 heaters, then we should use a specific range of pulling speed based on the optimization problem. So this is amazing that we can provide some machine learning information from an optimization problem. And if you look at the full solution of the optimization, so we have the initial case here. Y-axis is total energy consumption, and x-axis is the pulling speed. And it is obvious that we can optimize, we improve the process in terms of production rate and the energy consumption, and 2 material-related constraints. Let's have a brief look to the temperature and degree of cure evolutions from the optimization problem. We have temperature here and degree of cure and the axial distance during the pultrusion process. So in the reference or initial case, we have 3 heaters. So the company was using actually 3 heaters with a die length of 1 meter. And we proposed, with the same pulling speed, we proposed to use 2 heaters with a much shorter die. And this provides more or less the same degree of cure evolution if we compare it with the initial case. So if we look at the reliability-based process optimization, let's see what would happen if we change some of our constraints into statistical ones. Why should we do that? Because we have inherently in the process statistical variation in material properties and the process parameters. So we can do this by having an information on sensitivity indicator for the degree of cure with respect to various variation in process and material properties here. And now in our deterministic optimization problem, we convert two of our constraints into probabilistic one, such that during the process, the probability of degree of cure being less than 0.9 should not exceed 1%. And similarly, probability of having maximum composite temperature being greater than 240 degrees C should not exceed 1%. So let's see what comes out from the optimization results. I show you a plot for probability of mean degree of cure at the die exit. And this shows, this curve actually is the probability curve of the reference case where we have 200 millimeters per minute for the pulling speed. And let's try to understand the curve. So 0.9 here, this means that the probability of cure degree being smaller than 0.9 is 35% roughly. So we have 35% of chance that based on the variations in material properties, we might have a cure degree smaller than 0.9. If we apply a deterministic process optimization, obviously, incredibly we improve the pulling speed, but now with the statistics, we have a worse probability. Now we have 50% chance that the degree of cure can be smaller than 0.9. So let's compare the results of reliability-based optimization. Now we are able to shift these two curves to the right-hand side, such that now we have 1% chance, and still we improve the pulling speed substantially. And similarly, if you look at the probability of maximum composite temperature, so this is for the degradation, in the reference case, we don't have any risk that our material can degrade because all the temperatures are below 240. However, we would like to optimize our system for efficiency, for improved product quality. And this is the curve after deterministic process optimization. And now we optimize our process, but now we lose the robustness and the reliability because now we have approximately 47% of chance that our material can degrade during the process such that we wouldn't know. And with the reliability-based process optimization, we can shift back this curve to the position where now by considering all statistical variations, our temperature will not exceed 240, at the same time improving the pulling speed. Well, to summarize, these were the four aspects of professionalism in composite manufacturing. We actually need to characterize the material systems, develop constitutive material models, and translating them into numerical process simulations. And in the end, we need to optimize our process for improved product quality. We can do it by offline or online and taking the reliability aspects into account. With this, I would like to thank all my colleagues from Chair of Production Technology from University of Twente in Netherlands, Process Modeling Group from Technical University of Denmark, and Composite Materials Group from KU Leuven in Belgium. Thank you for your attention. I am ready for questions.
Thank you very much, Dr. Baran, for your nice presentation. So we have time for some questions. Does anyone would like to ask any question to Dr. Baran? I have one question about the pultrusion process.
Mm-hmm.
You have talked about us about the modeling of the process, the improvements in modeling, also in new curve sections. So how do you see the pultrusion process for sectors like automotive, for example, where apparently there are some parts that could be built with pultrusion? Which is your opinion about that?
Well, pultrusion is very popular and becoming more and more popular in, especially in wind energy and also in automotive sector. With the new advancements in pultrusion process, such as the curved pultrusion process, or the one that I know from Mondragon University with the band pultrusion, actually a mass production can be achieved for automotive industry. And I know from curved pultrusion, there is already applications, mass production applications in automotive industry for load-bearing products.
Hi, a quite nice talk. A question, do you foresee some kind of sensors, particularly for the online process? There is some kind of sensor that can check something during the process?
Obviously, yes. There could be more. I can give you some examples. For instance, the degree of cure. There are some applications with dielectric sensors for degree of cure. Obviously, for the pulling force, we can put pressure transducers to measure the pressure evolution during the process. And I think the easiest one by controlling the pulling force. If we monitor the pulling force during the process, we can relate the unexpected, increase or decrease in the pulling force with some of the process-induced defects.
More questions? Okay, so thank you again, Dr.
Thank you very
Baran,
much.
for your presentation.